I started the recording. So welcome today's lecture, Thursday, the 23rd of July. Let's begin with a few announcements regarding midterm number 2, Friday of next week. I did post a sample exam, so that's available. This time we'll just have one sample exam. Furthermore, regarding exam logistics, this time there is going to be a timer. That B Courses has this ability to put a timer. So once you look at the exam, then you have a certain amount of time to finish it. And to practice this principle, I prepared homework 8, part 1. So homework 8 will be split into 2 parts, part 1 and part 2. Now, in contrast to homework 7, where part 1 involved a significant amount of work, this homework 8 part 1 is really just a very quick calculation, but the point is, it is officially in the parlance of B Courses, it's a quiz. It's a B Courses quiz, and this gives us the ability to have a timer. So in summary, this homework 8 part 1, it's a B Courses quiz, and so as soon as you open it, now for this you'll have 2 hours, which is a huge amount of time for doing this integral. So the idea is not to have to rush through the integral, but we want to get some familiarity with this idea that we will need for midterm number 2. As soon as you look at the document, it starts a timer. Okay, and then you write your answer, you show your calculation, piece of paper, then you prepare a PDF file and you upload it. Okay, so that's what's coming up ahead for us. This thing will be due Tuesday of next week. Homework 8 is due Tuesday of next week. All right, so let's return to some physics here. As you know, in our last meeting, we talked about the fascinating motion of a free rigid body. So that's a rigid object with no external torques applied to it. Those are the words that are typically used. Internally, of course, there are interparticle forces. And if there are interparticle forces, and there must be interparticle forces to maintain the rigidity. So if there are interparticle forces, then there must be torques. So those are considered kind of interior. We don't have to worry about that because they simply enforce the fact that we have a rigid object, such as a tennis racket or a spacecraft, something like that. Okay, so that's why we have this term external, really emphasize a free rigid object, a free rigid body is an object with no external torques. All right, and we saw the remarkable result that a free rigid body, no external torques, no external forces, the behavior is very counterintuitive. And you can demonstrate this with a tennis racket or any other object that has 3 distinct eigenvalues. The intermediate axis theorem, we saw that for initial rotations. So if you prepare the system spinning about an axis close to the intermediate axis, then there's an instability. We have this exponential growth of the angle between the angular momentum vector and that axis. And it's exponential initially. Of course, it cannot go on forever as exponential growth. So what happens is it swings around and it goes to -1. Asymptotically times its original value. So to really understand that, we'll go into this discussion of Euler's equation. So this will be our first big topic today. And of course, what we did last time, we got some very good insights into the problem by looking at 2 conserved quantities. The kinetic energy is conserved and the length of the angular momentum vector. Those are conserved, and we studied the situation in the body frame. So that's the reference frame attached to the rigid object. So that's a non-inertial frame. So again, the notation, this is from our last meeting here. These are the axes that we'll use quite a bit. Shown in black, we have X, Y, and Z. Those, in this business, we typically call that the space frame. In chapter 9, we would have said it's the inertial frame, the lab frame. It's called the space frame. When you talk about rigid body motion, one speaks of the body frame and the space frame. So the body frame, this is a reference frame attached to the body. And so you can think of taking 3 toothpicks and sticking them into the rigid object. Those are these red unit vectors here. So E1, E2, E3. And so the angular momentum relative to the body frame, we speak of these coordinates L1. That's the dot product. We've got this E1 hat dotted into the L1 vector, etc. The crucial thing is, first you compute the angular momentum vector in the space frame, right? So you get a non-zero answer. In the body frame, the body is motionless. So it's not the angular momentum of the body relative to the body frame. It's the angular momentum vector computed in the space frame and then referred to the axes, these red axes. So you compute it in the space frame, then you transform it to the body frame. That's a rotation. That preserves its length. So the length of the angular momentum vector in the body frame is equal to the length of the angular momentum vector in the space frame. That's something we remarked here. The sum of the squares, right? That is a rank 0 tensor in the language of tensor analysis. We'll be contentious to call this scalar. It's a rotationally invariant scalar. So in the body frame, the sum of the squares of the components of the angular momentum vector, that's going to be a constant. Furthermore, the kinetic energy, we worked it out last time. It's very similar in structure. Notice the sum of the squares, but this time they have multiplicative prefactors. And so we looked at the implications. We saw that it led us to a fascinating problem in geometry. We contemplated the intersections between spherical shells and ellipsoidal surfaces. And there are some interesting things that can happen. Most notably the separatrix, right? That's when the radius of the spherical shell is equal to the intermediate of the three, what you'd call radii here. Okay, so in that manner, we saw that the motion of the angular momentum vector referred to these red axes. So we were interested in L1, L2, and L3. We saw that that necessarily was confined to certain one-dimensional curves. And these are curves, of course, on the surface of a sphere in that space, because this is a constant. So the remaining question is, how quickly does the angular momentum vector move along those curves? So we'd like to fully solve the problem. Remember, our goal in mechanics is to find the state of the system as a function of time. And right now we're interested in finding the angular momentum vector in the body frame as a function of time. Okay, that's an interesting milestone in the calculation. It still does not fully solve the problem. We'd like to ultimately know the angular orientation, the orientation of the rigid object relative to the laboratory frame. That's going to require some additional effort. So the first thing we'll do here, we'll start with a familiar result from the physics 7 sequence and or the physics 5 sequence, depending on which one you had. The time rate of change of the angular momentum vector is equal to the applied torque. Okay. So this is the time derivative. You see, that's a regular d up there's a regular d downstairs. This is the total time derivative. This is the angular momentum vector, and we'll use this notation we had in chapter 9. We indicate the reference frame like so. So what we're saying here is the time derivative of the angular momentum vector, and the reference frame is a space frame. So this is an inertial frame. And you know, if you're in an inertial frame, then this is the total torque. Capital gamma. That's a capital gamma with an arrow, right? It's a gamma vector. This is our torque vector. Now, many people are fond of using a tau for torque. Fair enough, it's a very popular symbol. But remember, we can't do that because we like to use tau for period. Okay, we have to use tau for period because we can't use capital T, right? Because we use capital T for kinetic energy. So there's kind of a domino effect here. We're driven to this madness here of using capital gamma for the torque, but basically it's the only symbol that's available here. Kind of being a little over dramatic there, but yeah, we'll go with the capital gamma. That's what Taylor uses. Okay, now we know one of the central results from chapter 9 if you have a time derivative of a physical vector, such as, here's this angular momentum, in the space frame, we can compute the time derivative in the non-inertial frame. Okay. Okay. So this result here, let's talk about this from several different perspectives. So first of all, you know, in chapter 9, we spoke of S naught and S. We had two reference frames. The S naught frame, that was our inertial frame, and the S frame was the non-inertial frame. So here we've adapted that notation. And again, in the theory of rigid body motion, when it speaks of the body frame, that's the non-inertial frame. It's attached to the body. Think of taking some toothpicks and sticking them into a rigid object. And then the space frame, kind of think of that as attached to the fixed stars, right? Basically an inertial frame. Another notable thing here, we're using lowercase omega. You remember in chapter 9, we used capital omega. And the reason was, in chapter 9, we had an organizing principle. Those capital letters, you remember at the very beginning of the chapter, we used capital A for the acceleration vector of the non-inertial frame relative to the inertial frame. And in the same spirit, we use capital V for the relative velocity. That's when we were talking about relative translational motion. Then when we got to rotational motion, we use capital omega, again, as an organizing principle to indicate that was the angular velocity of one reference frame relative to another. Now, in the theory of rigid body motion, one typically uses the lowercase omega for the angular velocity vector of the rigid body. That's just standard notation. So we're going with the lowercase omega here. And yeah, then you recognize this is one of the central results. We took this, actually this statement here, written in the notation of chapter 9 was a foundation concept. And then when we squared it, right, we perceived this as basically an operator statement in chapter 9. We squared it to get Newton's second law in the non-inertial frame, in the rotating frame. And in doing so, we got the Coriolis force and the centrifugal force. So this was a central equation there in chapter 9. So now we'll use it for rigid body motion. And you see we have the following very nice conclusion here. Okay. L dot plus okay, so let's put a box around this one. This is a great equation. Okay, so if you're looking for some good news, it's that we have first order time differentiation. Okay, that's welcome. That's some very good news. But let's take a second to talk about the notation. We're going to use the dot here for the time derivative in the body frame. Okay, so in the previous line, we had this very clear statement about which frame we're in. Let's make that even better with the improved handwriting like so. Okay, so again, this compact notation is helpful. Just the agreement that the dot is going to refer to the body frame. So what we have here is this portion of the previous line, I should say equaling the gamma, right? So really what we can do is emphasize that like so. So this stuff that I just indicated with the red ink, that's now put in this box. So we have the time derivative of the angular momentum vector in the body frame plus this omega cross L equaling the torque. And a special case is what we talked about last time. The free rigid body has a 0 for the torque. Let's just write that down. Okay, so that's a special case, the free rigid body. In general, you may have some, and you'll see this in some of the problems at the end of the chapter, you may have a spacecraft with some, they have these small rocket engines on the exterior to change the orientation of the spacecraft. So that's an example of how you would have an applied torque. And then the question becomes the motion of the system, right? And then, you know, historically, a fascinating story, which I mentioned earlier in the course, Neil Armstrong, before the Apollo missions, he was on a different mission, and they had a problem with the spacecraft kind of going out of control in the sense of spinning out of control due to one of these small rocket motors that got switched on and just stayed on. So when the spacecraft is spinning so quickly, there's a danger of losing consciousness. But Neil Armstrong was able to use a different source of gamma, so to speak, a different thruster. And then you see how confusing this is, right? When you're spinning around like that, trying to figure out which one will help you. So he was able to stop the rotation that way. So, yep, amazing but true stories. So now this will be our central equation. We're going to investigate some of the behavior that emerges here. And we've seen even when gamma is 0, you have extraordinarily fascinating behavior. And then there's all the cases where gamma is non-zero. All right. So this equation, like so, what we'll do is make a few remarks here. Now recall that the L vector, just a quick remark on notation here, recall. Okay. We had these unit vectors. Let's have a quick look here. A very memorable picture. Shown in red, we have E hat 1, E hat 2, E hat 3. Those are the unit vectors attached to the body frame. Okay. So we can write the omega vector as a linear combination of those unit vectors. Okay, fair enough. This is actually just the definition of these omega 1, omega 2, omega 3 coefficients. And then what we have here, because of the fact that we chose them to be the principal axes, we have these eigenvalues. So now the angular momentum vector, right, is equal to, remember the eigenvalues, lambda 1, omega 1, E hat 1. That is to say, if omega is equal to a multiple of E hat 1, if that's a principal, if that vector points along a principal axis, then you know that the angular momentum will point in the same direction, and the length of the angular momentum vector is gotten by multiplying by lambda 1. Okay, so that's our notation. And so you can see here, this collection, right, because this is a vector equation, it really encapsulates 3 individual equations, right, for the 3 components. So here's how, this would be one way you can write out the 3 equations. Okay, we're going to have 3 equations, and let's appreciate that these 3 equations can actually be gotten from one another by cyclically permuting the indices. Okay, let's see how that emerges here. So I've written the first equation. What we'll do next is increase all of the indices that you see with the understanding that if you go past 3, you have to wrap around and go back to 1. So let's write this down now. We're going to bump up all the indices one step. Lambda 2, omega 2 dot. Okay, so there's our second equation. And again, we got it from the first one just by bumping up the indices. Let's bump up the indices one more time. Here we go with the lambda 3, omega dot 3 minus lambda 1 minus lambda 2. Okay, wonderful set of equations here. And so let's appreciate that what we have done here is simply written out the components, right? Another way to say it is you take this equation here and you form a dot product with E hat 1. What happens if you form the dot product with E hat 1? Well, again, the dot is used for the time derivative in the space frame, body frame, and the lambdas are constants, right? These are eigenvalues. They are attributes of the mass distribution. So we really want to have some clarity there. The rigid object, whether it's a tennis racket or a spacecraft or what have you, has some attributes. And these the three numbers here, lambda 1, lambda 2, lambda 3, these are attributes of the object. So as well as the existence of the principal axes. So those, when I say attributes of the object, they are logically separate from other important numbers here, which is when you prepare an experiment, when you throw the tennis racket in the air, you provide initial conditions. So you determine the initial conditions. You also determine the initial kinetic energy, you know, the initial angular momentum vector, et cetera, and so forth. But these lambda 1, lambda 2, lambda 3, those numbers will be the same for any run of the system. So if you throw the tennis racket again, right, obviously we'll have the same lambda values. Okay, so to see how this occurs, we'll be interested in the number 1 component of this cross product. So there's a little bit of bookkeeping to be done. Again, the components of the angular momentum are these products. So you see lambda 1, omega 1, that's a product. That's a coefficient here in front of E hat 1 for the angular momentum. So you can go through this with the cross product, and these are the equations that emerge. And of course, the cross product has both plus and minus signs in there, along with all that bookkeeping you have for a cross product. And that's the reason why we have these various interesting plus and minus signs in the equation. Okay, so let's get some experience with these equations and see what kind of behavior can emerge. So we'll go through some examples here. Okay, so here's our first example. Suppose you have a spinning top with, let me write this out like so. A top is an object where it has an axis of symmetry. There's a little handle that you can hold between two fingers and then spin it. Okay, that's what we mean by spinning top. And so we're going to have the following assumption. Okay, that is to say, the what we would call gamma 3. Okay, we'll assume there are no torques about the axis of symmetry. Okay, and furthermore, a spinning top has an axis of symmetry, so 2 of these eigenvalues are going to be equal. So we'll have lambda 1 equals lambda 2. All right, so think of some of the recent calculations we did where we tried to visualize the eigenvalues of a tennis racket, of the T-handle. Remember, the astronauts on the space station have these T-handles. And so if you draw a similar picture for a spinning top, you can see that lambda 1 must equal lambda 2 if the symmetry axis, we'll assume the symmetry axis is the number 3 axis. Okay, so something wonderful happens here. If gamma 3 is 0, we have a 0 right here in this equation. Furthermore, if lambda 1 is equal to lambda 2, we have another 0. This is really good news. All right, you see the conclusion. The angular velocity vector projected onto the number 3 axis, that's omega 3. It's a constant, right? Because omega 3 dot must equal 0. So this is useful. Later in the chapter, we will have an analysis of this spinning top All right, these things are very popular, and we're going to see although the angular velocity could have some complicated behavior in terms of omega 1 and omega 2, it's very nice to know that it's exactly true here that the number 3 component, omega 3, of the angular velocity vector, this is a constant. So that'll be very helpful. Later in the chapter, we'll talk some more about the spinning top. Okay, let's again talk about the free rigid body. Remember we talked about the free rigid body here. Gamma 1 is 0, gamma 2 is 0, gamma 3 is 0. They're all 0. Total external torque is 0. Okay, so that'll be our next example here. Let's talk about the free rigid body, 3 distinct eigenvalues. So this is important when you talk about free rigid bodies. Last time we were talking about the case of 3 distinct eigenvalues. There was a lambda that was the largest, there was a lambda that was the smallest, and then there was the intermediate. Okay, so in order to talk about the intermediate axis theorem, you have to have 3 distinct eigenvalues. Okay, so we'll talk about the free rigid body. And furthermore, we want these eigenvalues to be distinct. So I'll just write them like this. Okay. So now, let's look at a special case. We're going to assume you have done the impossible. You've prepared the system, and I mean impossible kind of in quotes. I'll explain how I mean that. Assume you have prepared the angular velocity vector to point along one of the principal axes. So assume at t equals 0, we have an angular velocity vector that is purely along the number 3 axis. Okay, so omega 1 is 0, omega 2 is 0, and omega 3, let's have it be non-zero. Okay, so that says we have a non-zero omega 3. So when I said you have done the impossible, I meant that in the sense that if you, in the language of mathematics, if you choose a real number, say between -1 and +1, the probability of it exactly being 0 is 0. Okay. You only talk about intervals of probabilities. So in that sense, when you throw a tennis racket into the air, you're essentially choosing a random initial condition for it. It's extraordinarily unlikely, actually the probability is 0, that it's going to be exactly along a principal axis. Okay, you can try to get it very close. And we'll talk about how the error grows exponentially in some cases. But for this experiment, suppose you have prepared the system in this ideal state. At t equals 0, it's spinning about a principal axis. We're going to show that it continues to spin about that principal axis. So let's follow through the calculation here. So then, and let's be very careful, this set of equations here, we're talking about quantities in the body frame, right? Omega 1, omega 2, omega 3, those are quantities in the body frame. All right, so let's look at the implications. If omega 1 is 0 and omega 2 is 0, well, look at what happens here. This is certainly 0. You got 0 times 0. This is 0 because there's an omega 1. This is 0 because there's an omega 2. So all these terms here vanish. Furthermore, it's a free rigid body, so all the gammas vanish. This is really wonderful. Therefore, you see all of these omega component dots. They all vanish. We have omega 1 is a constant. Omega 2 is a constant. Okay, so we have, see, the thing is we want to be careful about the logic. These are considerations about what's happening in the body frame. And remember, this was a little bit of almost an artificial thing to do. We're talking about first computing the angular momentum vector in the space frame, in the inertial frame. Then you can imagine having someone hold a pointer in that direction and then have a little video camera attached to the body and observe that pointer. That pointer is going to move around in a funny manner. Okay, so viewing these vectors relative to the body frame. Okay, now in this case, we've solved this system of equations. We know that the solution is omega-1 is some constant, omega-2 is some different constant. Well, actually, we know there's 0. So these are constant and 0, and omega-3 is a constant that's not 0. Okay, so in the body frame, we have this constancy. Now observe how we can be very rigorous here. The next thing we'll do is observe. Okay, so this is logical implication. This arrow here indicates logical implication. Notice the angular momentum vector. In this case, it's a constant, and we know it's this constant here, lambda 3, right? Omega vector. This is constant. Okay, so this is in the body frame. Let's emphasize in the body frame. Okay, and now let's talk about rank 0 tensors, dot products. Well, in angles, right? When you have the dot product, we know the dot product, because it's rotationally invariant, an observer in the body frame will agree with an observer in the space frame about the dot product. And the result is everyone agrees that the angular momentum vector is parallel to E hat 3. If this is true in one frame, then it's true in every frame. So let's see if we can squeeze this in here at the bottom of the page. So we have the angular momentum vector parallel to E hat 3. Okay, and let's really emphasize there are two ways to look at this, right? In the body frame, obviously these 3 unit vectors are constant. Okay, and here we're saying in the body frame, this L vector simply points in the number 3 direction. Okay, let's take a second to remind ourselves how this looked in the picture we had last time. This was our picture from last time. Let's see, we'll fold it again like so. Last time, using energy arguments, right, the constancy of the kinetic energy and the constancy of the angular momentum vector, we know that the angular momentum vector in the body frame, so here's L1, L2, L3, we know that that is going to follow these curves. For the example that we're discussing now, it's this one here. You see that dot right there on the L3 axis? That's a solution. That's an equilibrium. The solution to the equation of motion is simply a stationary point right there. If you were to bump it slightly, it would move around this arc. But for the moment, we're considering the ultimate imperfection where you have achieved the dream here of having the angular velocity vector and the angular momentum vector parallel to the number 3 axis here. So I just wanted to mention, in terms of this picture, we're talking about that dot right there, which is where the sphere intersects the L3 axis. That's a solution to the equations of motion. Okay, and this happens to be a constant. Still, it's a perfectly good solution. And then this statement that we have now, the angular momentum vector is parallel to the E hat 3 unit vector. That's true in the body frame, but because you can express that using dot products, right? The dot product of the 2 vectors is equal to the product of the magnitudes. The same statement must be true in the space frame, okay? Now notice, in the space frame, I guess we'll need another piece of paper here. We're going to continue our dream here on the next piece of paper. So the next conclusion here, in the space frame, we know that the angular momentum vector is a constant. So we can conclude Okay, so in the space frame, this number 3 unit vector is a constant. And remember, you can think of sticking a toothpick into a potato, for example. This is what you should think about. These E hat 3 unit vectors, they're stuck to the body. And we know this one is constant. The other two are not constant, right? They revolve around. So E hat 1, E hat 2, not. Okay. But this is an important milestone that we have completely solved the problem. And when we say that, what we're saying is we'd like to know the angular orientation of the rigid object as a function of time. And so you can see how that solution is emerging now. We know that this E hat 3 unit vector is pointing in a constant direction. And we know that the angular momentum and the angular velocity point in the same direction. So these two here, we have steady rotation about the E hat 3 axis. So they're not constant. And furthermore, we have steady rotation about E hat 3. Again, everyone agrees that these are mutually orthogonal vectors. The reason is you can express that statement using dot products. Let's see, I think that's a little blurry. I wonder if the focus is better. Well, I'll admit it's not a very good 3 here. I'll draw a much bigger 3. Okay, there we go. So you see what we've done here? We have fully solved the problem. It was a two-step process. First, we were interested in the dynamics in the body frame. Remember the picture we had with the 3 axes, and the axes were labeled, for example, L1, L2, L3. Those are the components of the angular momentum in the body frame. And we have differential equations now that tell us about the evolution of the system in that body frame. Then in general, there's some effort, and we're going to explore this on the homework. There's some effort involved in reconstructing the motion in the space frame. That's a whole nother stage to the problem. In this case, we were able to do it with careful arguing, careful reasoning, using statements that are irrefutable. Nobody would deny that the dot product of 2 vectors in the body frame is equal to the dot product in the space frame because the dot product is a rotational invariant. Okay, so in that way, you see we carefully argued that this E hat 3 unit vector in the space frame is pointing in a constant direction. Furthermore, the angular velocity vector points in the same direction, and that means the other two in the space frame, they rotate steadily about that. And of course, the right-hand rule governs this part of the solution. You point the thumb of your right hand in the direction of E hat 3. Now your fingers of your right hand curl around and they tell you the sense of rotation. So E hat 1 and E hat 2, they rotate in a plane perpendicular to the E hat 3, and the angular velocity is omega. So that's a complete solution now. Yeah, wonderful solution for this very special case. Okay. So now we're going to delve a little more deeply into the intermediate axis theorem. Okay. Last time we made it plausible. We provided a very compelling story. When we drew this picture, right, a picture is worth 1,000 words, as you know. When we drew this picture, we had essentially proven the intermediate axis theorem, right? Because these red curves, we argued the angular momentum vector relative to the body fixed axes is confined to one of these red curves. But the argument we presented using conserved quantities, we couldn't tell how quickly or slowly, or if at all, the angular momentum vector was moving, right? In fact, it moves around on this sphere according to a certain vector field. And later in the course, when we talk about the Hamiltonian formulation of mechanics, we'll be interested in so-called velocity vector fields on phase space. We'll define phase space. It's a higher dimensional space, pretty much equivalent to our notion from Lagrangian mechanics of the space of classical states. So phase space is basically, for many problems, you have the union of all this information about positions and momenta. So it's a 6-dimensional space for a point particle. You've got x, y, z for coordinates and px, py, pz. But in general, phase spaces are 2-dimensional. We're going to see that the surface of this sphere is a 2-dimensional manifold. It's not a plane, it's the surface of a sphere. But we're going to see you can draw a vector field on this sphere so that this motion is Hamiltonian, and that's something we'll make rigorous later in the course. Okay, so the vector field provided here is essentially what we worked out earlier today. Right? These equations, now notice it's phrased in terms of lambda 1, omega 1 dot, but we know the product lambda 1 times omega 1, that's L1. Okay, so we could have written capital L1 dot here. It's exactly the same thing. In fact, I can just scoot down the paper. You see, the first component of the angular momentum vector is lambda 1, omega 1. That's capital L1. So this, for the free rigid body, of course, you got zeros here on the right-hand side. And these omegas, you can eliminate them in favor of omega, capital L, sorry. And so this becomes a very nice system of equations that describes a vector field that's tangent to this sphere, right? We know the angular momentum vector must stay on the surface of the sphere. And so at that point, you can truly figure out how quickly or slowly it goes around here. And furthermore, you can see that the separatrix over here at this endpoint, there are 2 of these curves where the separatrix moves the system towards the stationary point, and the other 2 move away. So this will be an example that we'll discuss in more detail, the notion of stationary and stable and unstable manifolds, right? Something we've talked about before. Okay, so what we're going to do now is return to this discussion of the intermediate axis theorem. Okay, here we go again with the intermediate axis theorem. Let's save ourselves some time by using appropriate paper weights to hold it in place because the paper wants to bend. Okay. There we go. So this is something we talked about last time. It was a wonderful opportunity to build up some experience with eigenvalues. We argued that this lambda 3 was the smallest. If you rotate the tennis racket about this axis here, the relevant moment of inertia is this lambda 3, and that's the smallest of the 3 eigenvalues. Okay, and again, this lambda 1 is the largest. That's what we talked about last time. Okay, what we want to do now is, as always, what discussion would be complete without a series approximation? We're going to have a notion of different orders and smallness. And in particular, we're going to say initially omega 1, and so that little 0 means at time t equals 0. So these 3 things are functions of time. Omega 1 as a function of time, omega 2 as a function of time, etc. So when you put in 0 for t, what we're saying is that t equals 0, omega 1 is small. At t equals 0, omega 2 is small. And at t equals 0, omega 3 is not small. That means we have initially, so the initial conditions for this problem are the tennis, can be stated as follows. The tennis racket is spinning approximately about this axis. And as I mentioned, oftentimes on the tennis court, you'll see players when they're waiting for their opponent to serve, they're doing precisely this. They're spinning their racket about this axis, basically saying, hurry up and serve the ball. I would like to play some tennis here. So yeah, now if you do this on the space station, what we're saying is you have a tennis racket, you spin it, right? When you launch it, you impart some initial conditions on it. And we're saying the initial angular velocity vector is very close to being parallel to this axis, okay? So that's a verbal description of these initial conditions. The important thing is to perceive that statement as a statement here about the initial conditions of the angular velocity vector. And again, when we say 1, 2, and 3, We're talking about the components relative to the body frame. Okay, great. Now we have our initial conditions. We have our differential equations, right? This big rectangular box. Those are the equations we must solve. Okay, so we're going to continue here like so. Okay. So this analysis, what we're doing here, the picture I just showed you, we have the free rigid body. And the initial conditions, the angular velocity vector, let's go to like this, angular velocity vector initially almost parallel to okay, so this is the problem we'd like to solve, the initial conditions like so. Well, if that's true, let's see what kind of equations emerge. Okay, let's start by looking at our third equation here. I'm pointing at it with the pen. Again, all the gammas on the right are 0. We're going to say some words that we love to say. This product here is second order in smallness, right? Because that's omega 1, that's omega 2, okay? That's second order in smallness. We argued that both of those are going to be small. So this is second order in smallness. We're going to call it 0, okay? Therefore, I'll write down that observation we just made. This omega dot 3 is second order in smallness. Okay, so we're going to ignore that, right? Because it's quadratic. These are both small. Omega 1, initially small, that's small. Second order in smallness. Therefore, so here's the arrow for logical implication. Omega 3, for all intents and purposes, omega 3 is a constant. Okay, great. Well, this is some really good news. It means I can eclipse this equation like so. We have 2 equations remaining, and look at the structure that emerges here. Again, we've got zeros here on the right-hand side. We have omega 3 as a constant. Okay, now something wonderful happens. If omega 3 is a constant, and of course the lambdas are constant, then we have a statement that omega 1 dot is a constant times omega 2, and omega 2 dot is a constant times omega 1. This is wonderful. So we can immediately take these 2 equations. Now, what would you do if you were faced with those 2 differential equations? Remember, omega 1 dot is a constant times omega 2. Omega 2 dot is a constant times omega 1. Well, you simply differentiate one of the equations and plug in. So you get a second order differential equation like so. Omega 1 double dot. Okay, we've got a big impressive constant here. So therefore the large square brackets, lambda 3 minus lambda 2, lambda 3 minus lambda 1, okay. And once again, all that work we did in chapter 5 is going to pay off for us, because this is precisely the kind of thing we did in chapter 5. You're trying to solve a differential equation, and the statement is that the second time derivative of a function is equal to some sort of constant times the function itself. Right? We know there are 2 cases depending on the sign. You can have oscillatory solutions, or you can have exponentially growing and exponentially decaying solutions. Okay, so let's be very clear. The thing inside the square brackets, see how careful I use the square bracket, sorry. the curly braces, I use curly braces to indicate the square brackets. We're going to call that capital C. Oops. That's supposed to be a capital C. So we have omega double dot equaling minus capital C times omega 1. Omega 1 double dot, negative sign, constant, omega 1. Okay, so we know very well what happens next based on chapter 5. If C is positive, right, you have basically a Hooke's law restoring force, right? In terms of all the mechanics problems of chapter 5, think of a Hooke's law restoring force. You have oscillatory solutions. Then this function that we search for, omega 1 of t, that's the function we'd like to figure out. This is oscillatory. Okay. And conversely, if C is negative, what do we know? Okay, so then what we have here, it's a linear combination of an exponentially growing and an exponentially decaying, right? So we might as well just write it out in terms of mathematical symbols. We have an e to the plus alpha t plus some other coefficient e to the minus alpha t, right? Where this alpha is the square root of minus c, okay? If c is less than 0, then minus 1 times c is positive, and you're welcome to take the square root. No one will complain about that. So in that sense, this alpha is a real number. So you see we have exponentially growing and exponentially decaying solutions. Okay, so now the remaining task here, the key to understanding the intermediate axis theorem here lies in this funny arrangements of the 1s, 2s, and 3s here. Okay, so let's appreciate the statement that has emerged here in front of our eyes. Okay, and it is the following. Now, when we drew the picture of the tennis racket, remember when we talked about the tennis racket, we had chosen lambda 3 to be the smallest, etc., lambda 1 the largest. Okay, that was for that picture. But now we're going to reinterpret what we just said. The calculation we did here is completely valid. Remember, the only assumption was that the omega vector is initially almost parallel to e hat 3. We have not made any assumptions about any one of these lambdas being larger or smaller than any of the others. Okay, so therefore we can take this result here and we can examine various cases. Okay, in particular, we can examine the case, all right. So consider okay, I'll put the paper like this. As I said, we have not yet utilized any sort of assumption about any of the lambdas being larger or smaller than any others. So now we're free to reinterpret the lambda 1, lambda 2, lambda 3. So consider the case where, let's put it like this. Consider the case where lambda 3 is intermediate, okay? So lambda 3 okay, now let's look at the logic. Either lambda 1 could be the largest or lambda 2 could be the largest. We're not so concerned with that. Either one could be the smallest. We're just saying lambda 3 is in between. So one scenario is lambda 1 is the greatest, then comes lambda 3, and then lambda 2. Another scenario, lambda 2 is the greatest, then next is lambda 3, and then lambda 1 is the smallest. This is what we mean by intermediate. Okay, what happens here? Well, you have lambda 3 minus lambda 2, and lambda 3 minus lambda 1. Okay, so thinking in terms of relative displacements, one of these factors in the numerator, right? In the numerator, we have two factors enclosed in parentheses. Exactly one will be positive and one will be negative. Now the lambdas themselves are always positive, so the denominator is positive. So we've proven that in this case, C is negative. All right, there you have it. This capital C is less than 0. So in summary, what we have shown, if lambda 3 is the intermediate eigenvalue, if it's between the other two, then the capital C is less than 0. And then we have this scenario here, the exponential growth and the exponential decay. All right. In the other cases have this scenario, the oscillatory. Okay. And so to summarize here, we have the picture of the tennis racket. Next time you're in space, bring a tennis racket and do this. Spin it about an axis that's near this axis here. You'll see that's stable. It might wobble a little bit, but it generally will stay near this axis. Spin it about an axis that's near this axis here. And this you can actually easily do on a tennis court. You pretty much need to throw it in the air, but the center of mass motion, that's a separate question, right? And again, this is stable. It might wobble a bit, but it's stable. But if you try to spin it about this axis here, and believe me, I've tried, you can typically, on a good day, you can get 2 complete revolutions before that exponential growth kicks in. And that's pretty rewarding when you achieve that. To see this thing floating in front of your eyes and spinning about this number 2 axis for 2 revolutions is pretty amazing. Then, again, that behavior is going to kick in. The small error that really was not spinning exactly about the number 2 axis, that small error starts to grow exponentially and it flips over. Okay, so yep, amazing result there with the intermediate axis theorem. Okay, so let's now talk about some more complicated cases of rigid body motion. Okay, this analysis here is basically in Taylor's book, but here's a problem that's not in Taylor's book, and let's see how a careful analysis of this problem will rest upon our knowledge of foundations concept like the instantaneous axis of rotation. Okay, so here we'll go onto a new piece of paper. All right, again, a very popular problem if you have a coin rolling on a table. Okay, let's look at the case of a coin rolling on a table, horizontal table. Okay. So this is, again, it's a fun problem because you have to be very careful with all the definitions we have. And again, there are some surprises along the way. So first, let's draw a picture of our basic setup. This one's going to be a perspective view. Well, frankly, I can save us some time here by reusing my diagram, which I have here, which is in the notes. Let's do this. Okay, we're going to go for this approach here. So we have this coin rolling on a table. It's a circular path. Okay, so the coin is leaning slightly. We're going to talk about that. And computing that angle is going to be important to us. But let's observe a few things here. We're going to have to introduce some notation. And notice we do have a capital omega. The reason we're doing this is we're going to continue to use the lowercase omega for the instantaneous axis of rotation. In other words, the lowercase omega is a vector that points in along the instantaneous axis of rotation. So it carries that information. And furthermore, the magnitude of the omega vector tells you about the rate of rotation about the instantaneous axis of rotation. Okay. The surprising thing here is that we're going to see the instantaneous axis of rotation is in a remarkable direction because anytime you have problems with rolling, okay, and this is a case of no slip rolling, we have an instantaneous axis of rotation that contains the point of contact. Now, you know, earlier in the course, we said some alarming things about no-slip rolling. In general, problems with no-slip rolling can bring in non-holonomic constraints. But again, for this problem, we're assuming it's a circular path. We have an ongoing state of affairs. The center of mass of the coin is going around a circular path in a uniform manner, okay? What you have here drawn on the surface of the table, you have the path of the point of contact, okay? So if you were to watch a movie of this coin rolling around in a circular path, the point of contact is defined for every frame in the movie. And here we've simply marked all those points of contact on the surface of the table. So that there's a circle drawn on the surface of the table. Notice that the center of mass of the coin also moves in a circular path. It's above, it lies in a plane that's parallel to the table, but is above the table. And the radius of that path is smaller because the coin must lean towards the center to, in order for this motion to continue in a steady state. Okay, so we have to introduce this capital omega. What that is, the definition is you focus your attention on the center of the coin. It's executing uniform circular motion, okay? And capital omega, and of course, we're using the right-hand rule as always. This loopy arrow indicates that the motion is counterclockwise as viewed from above. So the center of the coin is going around the table, around a circular path that lies in a plane parallel to the surface of the table, but is above the surface of the table. Okay, fair enough. So let's now analyze some of the fascinating implications and let's see, I have some notes. I'm trying to avoid PowerPoint overload. So avoiding PowerPoint overload, we can go like this. Yep, we can go like this. We don't want to get PowerPoint overload. So here's the situation, and the colors really, I can tell you there are colors on my paper, but they don't seem to come through too well. So the remarkable thing here to appreciate is that the instantaneous axis of rotation goes through, okay, at an angle like this. And here's where you can do a wonderful thought experiment, okay? We're thinking of a coin that is made from a uniform material. So the surface, you can think of it as infinitely thin, and there's a surface mass density similar to in electrostatics when you talk about surface charge density. Here we're assuming, you know, take a piece of sheet metal that has a uniform mass distribution and cut a circle out of it. That's what we're talking about for this experiment with the coin. Okay, so the center of mass is at the center of the coin. And now it's useful to think about the following thought experiment. Take a piece of styrofoam, which we're going to assume is massless but rigid. Okay. Take a piece of styrofoam and attach it to the coin. And you see this line segment from the center of the coin over here to the axis of rotation. Think of that as being made of styrofoam. So it's part of the rigid object, right? But it's massless. It does not affect any of our calculations. We're going to talk about moments of inertia, et cetera, and so forth, center of mass. The important thing is we've proven that the instantaneous axis of rotation goes through the picture diagonally like this. And the reason is you have this point of contact down here. The instantaneous axis of rotation must go through there because that point, if it's a point of contact and you have no slip rolling, then that point is motionless, okay? If that point is motionless, it's on the instantaneous axis of rotation. And furthermore, this piece of styrofoam, which we attach to the center of the coin, because we have assumed we have this steady rolling motion along a circular path, then this portion right here of the styrofoam is also motionless. And that's enough to fully define the axis of rotation, okay? It must be true that the axis of rotation is this dotted line, which remarkably passes through the picture at an angle like so. This is the instantaneous axis of rotation of the mass distribution. This capital omega here, we've talked about just one point, the center of the coin. The center of the coin is executing uniform circular motion about that axis of rotation. fair enough. But other molecules in the coin, they have a much more complicated motion. So the coin, thought of as a rigid object, has an instantaneous axis of rotation. And now we can see our wonderful lowercase omega vector here. The lowercase omega vector points along this instantaneous axis of rotation as per its definition. Furthermore, this point here, which is capital cursive O, the origin, right? This point is motionless. Again, it's useful to think of a piece of styrofoam glued onto the coin. That styrofoam then is very much a part of the rigid object, as are the actual molecules of metal in the coin. And this point on the styrofoam is motionless. Okay, we're going to call that cursive capital O. That's the origin. All right. The omega vector, the lowercase omega vector, must point along this instantaneous axis of rotation. Okay. So now there are some parameters. We're going to use this angle alpha. This is our lean angle. Lean. It's the angle at which the coin is leaning. Obviously, we referred it to the vertical. And in this view here, notice if this view is edge on. Okay. The upper picture was a perspective view of the problem. This view is edge on. The coin is edge on. The table, the surface of the table appears as a horizontal line. Again, capital R is the radius of the path on the table. The center of mass of the coin is way up here. The radius of its motion is smaller. And we're going to introduce this lowercase b for the radius of the coin. All right, so the really important takeaway message here is the instantaneous axis of rotation is meaningful, okay? If you have a rigid body in some arbitrary state of motion, and we're assuming some non-zero rotation, if it's just sitting there doing nothing, then you do not have a well-defined axis of rotation. But if there's any sort of non-trivial rotation taking place, then at any instant, we have an axis of rotation, okay? And notice the argument that we use here for this coin. We identified the instantaneous axis of rotation. And of course, that governs all the molecules in the coin, right? Notice the coin has some molecules way down here close to the table. There are some way up here far from the table. And then there's the so-called leading edge and trailing edge. Now notice as you view from above, you're going to see those molecules with a very interesting motion. All of that motion, because this is a rigid object, all that motion is fully characterized by this instantaneous axis of rotation. So for one instant, this is our axis of rotation, and we know what that means. We know the velocity vector of any point in the coin. It must necessarily, at that instant, move in a circular path about this instantaneous axis of rotation. And now we have a complete description of all the velocity vectors of all these points inside the coin. Again, this omega vector in one fell swoop, this plus the useful relation, right, omega cross r, tells you the velocity vectors of all those things. So the next crucial thing here in this discussion is to figure out the angular momentum vector. Okay. One thing we have shown here at this point is the angular velocity vector traces out a cone. So this is lowercase omega. This is the angular velocity vector of our mass distribution. Okay. And it sweeps out a cone. Like, I don't know if I can do this on the document. Yep, it's actually surprisingly difficult to do, but I'm trying to sweep out a cone. Yep. Well, I guess I could try like this. Problem is the pen cap will run into the table. Yep, I'm sweeping out a cone pretty well. Yeah, see how I'm sweeping out a cone? Yeah. So the lowercase omega vector, which is crucial for our formulation of the problem, the lowercase omega vector was in those equations that we wrote down. That's the instantaneous angular velocity. And we know for this problem that it precesses, right? Capital omega is an angular velocity. It's not the angular velocity of the body. It is the angular velocity of this central point in the coin about this vertical axis. So much is true, but it is not the angular velocity vector of the entire rigid object. There's only one angular velocity vector of the entire rigid object, and it's this lowercase omega vector, which points like so through the picture. Okay, so we have a couple of very important statements. this cursive capital O, this is the origin for our analysis, right? This point on the rigid body, with the understanding that we've attached a massless rod, so we can really appreciate that this point is a motionless point on the rigid body. And furthermore, the instantaneous angular velocity vector, this lowercase omega angular velocity vector, it precesses at this rate, capital omega, it sweeps out a cone. What we're going to show next is that the angular momentum vector, right? We haven't drawn the angular momentum vector yet, but we know there is an angular momentum vector. At any instant, this coin has an angular momentum vector about this origin. And furthermore, we know that that angular momentum vector is gotten via matrix multiplication from this lowercase angular velocity vector. Okay, so the next order of business is to figure out the moments of inertia of the coin. Right, now that's a special rigid object, right? And you know from your first year physics course, if you have a circular disk, we can write down a nice formula for the moment of inertia about its own symmetry axis. And then there's a different formula if you have an axis of rotation that lies in the plane of the coin. Again, that's a principal axis. Okay, so those are well-known results. And in a similar manner, you can come to a full description of the moment of inertia tensor for this mass distribution. It must be the moment of inertia tensor about this origin, because we want to use our most fundamental result, which is that the angular momentum vector is a matrix times the angular velocity vector. And we're going to see that the angular momentum vector traces out a cone, it sweeps out a cone, just like this angular velocity vector does. So I haven't shown it in this picture, but the angular momentum vector sweeps out a cone. At that point, we're in a very good position to explain everything that is going on in this problem. Once you show that the angular momentum vector is precessing, it's tracing out a cone, it's precessing, you can use the fundamental result that the time rate of change of the angular momentum vector in the space frame is equal to the applied torque. Now here we do have a torque, right? There's a point of contact here, okay? There must be some friction. This cannot be a sheet of ice, right? You can see that because the center of this coin is executing uniform circular motion. There must be a force in the horizontal direction. If this were on a sheet of ice, the center of mass is definitely not going to go in a circle, right? So yeah, there is definitely friction. We have no slip rolling here, which provides a frictional force in the horizontal direction. Then you have the gravitational force straight down. That's balanced by the normal force from the surface. So those cancel out. The center of mass does not accelerate upwards or downwards. So that's something we can say. And then the final kind of icing on the cake, so to speak, is this calculation where you look at the angular momentum vector, and we've proven that it precesses about this vertical axis with this frequency, capital omega. Okay. Then you just bring in this knowledge that the time rate of change of the angular momentum vector in the space frame is equal to the applied torque. Okay. So that's a powerful, powerful kind of prescription for solving this problem. Now, some of this stuff gets rather technical, so let's just appreciate the important concepts. Let's go through this and looking at some of the important concepts. Okay. So, using the notion of vector addition, okay, one of our foundation skills. We're going to write the angular velocity vector, right? We showed the angular velocity in that picture a moment ago. The angular velocity vector, we'll write it as the sum of two terms. And let's, we need some sort of name for these two terms. Okay, so this is something we've talked about in recent homework assignments too. It's a decomposition. Anytime you have a vector, you can decompose it and write it as a sum of two terms, one of which is parallel to a certain plane and one of which is perpendicular to a certain plane. Okay. And so the idea is with the moment of inertia tensor, let's see how we can phrase this. Let's talk about the moment of inertia tensor here for a second. So recall the following facts. We're going to talk about this vector decomposition in a second. So recall, if you have a uniform circular disk, we can begin to tabulate a bunch of statements that we know to be true. So first of all, here's a uniform circular disk. This is shown in perspective. So on the paper, it looks like an ellipse, but it's a perspective view of a uniform circular disk. And here's some shading to really make it clear. This is the coin. Okay. We need to talk about the principal axes. Okay, so we know okay, so this is a principal axis. And furthermore, this has a very large eigenvalue. So this is a principal axis, and our abbreviation PPL is a big time saver, principal axis. And we know that this has the largest eigenvalue, right? We talked about this recently. To get the largest eigenvalue, you want to have the mass as far away from the axis of rotation as possible. So this one has the largest lambda. We're using the lambdas for the eigenvalue. Okay, and the results are tabulated. It's probably 1/2 mass times radius squared or something like that. Now, we have another principal axis. And the way to, by the way, as you know, the way to convince yourself that this is a principal axis is do a thought experiment where you spin this disk about that axis and compute the angular momentum about the center of mass. So you can see if you have an omega vector pointing straight up, so this is spinning counterclockwise as viewed from above, then the angular momentum vector is pointing straight up. Okay, so that's a principal axis. Here's another principal axis. Okay, that too is a principal axis. In fact, any line you draw straight across the circle is a principal axis. Okay, and so this is a case where we have an eigenspace, a two-dimensional eigenspace. This is a principal axis, and lambda, we can say with certainty that lambda is less than this largest one. If my memory serves me, it's 1/2 of that largest one. So lambda is less than okay. So these are things that we recall from our first year physics course, but now we want to bring them into our chapter 10 knowledge. And we want to start making statements about the moment of inertia tensor. So what we can say is the following. Although there's a freedom to choose, right? There's some arbitrariness here. We must choose the 3 unit vectors, okay? So what we've done here, this portion of the paper was devoted to some fond memories from our first year physics course, okay? Now we must assimilate this information into our understanding of chapter 10. So we must choose we have to choose the 3 unit vectors. And you see there's some arbitrariness here. But the point is you must choose 2 vectors in the plane of the disk. That's the coin in our problem. You must arbitrarily choose 2 vectors in the plane of that disk. It is a 2-dimensional eigenspace. Those 2 directions have the same eigenvalue. It's this one here. It's the one that's less than the larger one. So you see, this is not a case where we have the intermediate axis theorem, because we don't have three distinct eigenvalues. We have this largest eigenvalue, and if you have that be the number 3 axis, then by all means, there's your E hat 3. There's not much controversy there, but you must choose, and again, you could get a small paintbrush and actually paint this stuff onto the disk. And in my office, I have some objects where I actually have gotten a permanent marker and marked axes on there. Okay, so there's some arbitrariness here, but there's a two-dimensional eigenspace. So you must choose a basis, the E hat 1 and E hat 2. Then in our next meeting, we'll talk about this vector decomposition. Once you do the decomposition, then the calculation of the angular momentum vector is trivial, right? Because there's one eigenvalue for one of these two terms in the sum, and there's a different eigenvalue for the other one. Okay, so we'll be able to get the angular momentum vector of that coin using this framework, and all the while exercising and cementing our understanding of chapter 10 material. Okay, so we've passed the 2 o'clock. I'm going to stop the recording, but I'll stay here for questions.